now we want to take a quick look at some examples and then look at the inverse Z transform. Let's take a couple of quick examples. Okay, this is an example which helps us understand the autocorrelation aspects in a clear manner. Supposing we are given that x of n is equal to a power n u of n, then we know that the Z transform x of z is 1 over 1 minus a Z inverse mod z greater than mod a. That's the Z transform, and we will assume that mod a is less than 1, because only then you can get a causal sequence. It will be a decaying exponential. So mod a less than 1. Okay, so now looking at this, tell me where the poles and zeros are. You have a pole at z equal to a. And don't forget, remember, we have to look at the rational form. There will be a 0 at z equal to 0. So if you were to draw this diagram, this is the unit circle. Okay, there is a pole at z equal to a. There is a 0 at z equal to 0. The region of convergence, look at the circle with radius r equal to a, and region of convergence, if you take it to the right, you will get a right-sided sequence. Okay, that is the interpretation of what we have in terms of sequence. So again, this is only to sort of bring all of the Z transform concepts together. Now, would like to compute R xx of n, and so this has got a Z transform R xx of z, which is given by x of z times x of 1 by z. Okay, and we can write down this expression as 1 minus a z inverse multiplied by 1 over 1 minus a z. You replace z with 1 over z, so this becomes z. What is the ROC? The ROC for the first term, this is mod z greater than mod a. For the second term, again you can look at the expression that we have, mod z is less than 1 over mod a. Okay, so basically these are the limits of that. So the intersection of these two both have to be satisfied. So if this is a, 1 over a will be at a point outside, and if you draw a circle with 1 over a, okay, this is 1 over a, the location between the two circles becomes the region of convergence for the autocorrelation function. Okay, so if this is a, this is 1 over a, then the region of convergence for the autocorrelation function is between the two circles, the red dash circle and the green circle. So mod z greater than modulus of a less than 1 over modulus of a. That is the ROC for the autocorrelation function. And again, a very simple example, all we wanted to emphasize was how do you get the expression for the autocorrelation and then give the interpretation. Now, there is a second or an extension to this question. Okay, give a sequence, another sequence. Okay, give me another sequence x1 of n, which has the same autocorrelation function. Another sequence x1 of n that has the same autocorrelation function. Okay, I want to have Rxx of z to be equal to 1 over 1 minus a z inverse into 1 over 1 minus a z. Same autocorrelation sequence. Okay, same autocorrelation sequence. That means Rxx of n has to be the same, and so such that Rx1 x1 of n equal to Rxx of n, and this also indicates that Rx1 x1 of z must be equal to Rxx of z. Give me another sequence that has the same value. Okay. And one of the interesting results that we have from our properties is that look at a time shifted sequence x1 of n equal to x of n minus n naught. Okay, what will x1 of z be? X1 of z will be equal to z power minus n naught x of z. Okay. Now, remember, if you want to get the autocorrelation of x1 of z, then you must also get x1 of 1 by z. Okay. When you do that, you find that what you get is z power n naught times x of 1 by z. Okay. Now, combine these two and look at what is the r x1 of z. So basically x1 of z multiplied by x1 of 1 by z can be verified is equal to x of z x of 1 by z. So a time shifted version will have the same autocorrelation as the original sequence. No change. Okay, and something that we may have had to, plot the sequence, look at it in terms of the autocorrelation, and then try to figure out. But we were able to get the answer very quickly without any difficulty because we looked at it in the Z transform. Z transform is the same, so therefore the autocorrelation has to be the same. So sometimes it is easier for us to look at a result in the transform domain and then come to a conclusion in the. So let's make it a little more interesting. Give me one more sequence, another sequence x2 of n that has the same autocorrelation sequence. Okay, what other properties can we use that has the same autocorrelation as x of n? Autocorrelation as x of n. Okay. Now, one more property that we can verify is that the autocorrelation is x of z, x of 1 by z, product of those two terms. Okay. Now, what is the sequence corresponding to x of 1 by z? It is the time reverse sequence. So, can we take x2 of n to be equal to x of minus n? It's a valid answer, valid possibility, right? It's a different sequence, time reverse sequence. So what is r x2, sorry, let's write x2 of z. x2 of z will be equal to x of 1 by z. Okay, and then we look at r x2 of z will give us a product of x2 of z and x2 of 1 by z. That will give us x of 1 by z and x of z. Okay, of course you can, and the ROC in both these cases will be exactly the same as the original ROC. Now, what is the key takeaway from here? You're starting to see some of the benefits of looking at a problem in the transform domain. Now, here again, we have been able to get some insights. The delayed sequence has got the same autocorrelation. The time reverse sequence also has the same autocorrelation. Okay, something that you may not have immediately guessed it, but it is something that is a powerful result. And this actually goes back to the fact that Rxx, remember we said verify Rxx of minus n is equal to Rxx of n. Okay, now again, this property has come into this second example, part B, where we said, okay, the time reverse sequence, because the original sequence is actually is an even function, we can relate it to the result that we have obtained in terms of the observation that we have. All right, so we are ready to look at some of the more important aspects, and to prepare for our discussion on the inverse Z transform, a couple of more results will be helpful for us. So here is that additional result, some results that are useful for us to make a note of, so that we will then be able to. So let x of n be a real valued sequence. X of n is a real valued finite length sequence. Finite length sequence. Okay, what can you tell me about x of z? X of z will exist. It will have the entire z plane with the possible exception of z equal to 0 or z equal to infinity. Okay, so let us assume that we have a causal sequence. So x of n, I related to the z transform. X of z, what you will get is you will get a polynomial of a certain order. Let us say the order is equal to n. So n equal to 1 through n, you will get a polynomial of order. You can factorize it, and you can factorize it and say that the factors are 1 minus ck z inverse. So basically you have a product of n factors that is representing the z transform. All right. Now, since we are given that x of n is real valued, okay, then we can make the following statement, that ck must be real valued. That is one possibility. Or the ck and ck conjugate must be the roots. Must be roots of x of z. Okay, why do we say that? Take the product of 1 minus ck z inverse. Ck is conjugate, it's a complex number. 1 minus ck conjugate, if that is also present, that is another 0. Expand this, what you will get? 1 minus 2 times the real part of ck times z inverse plus mod ck whole squared z power minus 2. Notice that if you have a complex conjugate pair of roots, that product will give you a polynomial with real coefficients. So for example, this is real valued, right? Of course, this is trivially real valued, and this is also real valued. Okay, so this is an important element for us to keep in mind. So when you have a real valued sequence, the corresponding z transform, what I have written down is in the context of the zeros. It will either occur as real valued zeros or as a pair of complex roots.
So product k equal to,
I'm sorry?
Product k.
Oh, I can change that. Yeah, I should change this to n. Thank you. This should be Cn. Yeah. I think I've been using, suppose I've been using k. Maybe I should use k here also. Yeah.
And causal.
I'm sorry?
Causal.
Finite length sequence and causal. Yeah. All right. So now I want you to look at what are the corresponding implications for the autocorrelation of x of n, where x of n is a real valued sequence. So we say that Rxx of z will be equal to x of z x of 1 by z. Okay. Then what we recognize are that for x of z, you will have ck and ck conjugate as the roots, if assuming they are complex valued. Then this term will give you 1 over ck and 1 over ck conjugate. Okay, so the autocorrelation sequence will have the following combination of poles and zeros. Doesn't matter which one. Both will have satisfy the same property. You will get CK conjugate 1 over CK 1 over CK conjugate. Okay. Or if it were real valued, then you will get Cj and 1 over Cj. Okay, this is very, very important, because what we are saying is the autocorrelation sequence, if you were to look at the location of the poles or zeros, will look like this. You will get all the 4 combinations, right? You will get D1 conjugate, 1 over D1, 1 over D1 conjugate, or you will get the reciprocal locations. So this is a useful thing for you to keep in mind, because we are going to be leveraging this in our study today.